Hello everyone, my name is Saleh Al Khalifa. I'm a Senior Manager of Data Science, and the topic of my project here is known as Towards Transparency in Black Box Models, Investigating Methods in Explainability for AI Systems. So to go ahead and dive into the contents of this project today, the real focus point here is the use of artificial intelligence in many different types of critical domains. Over the last several years, we've seen an increase in the use of AI and machine learning models in many different industries, including biopharmaceuticals, healthcare, manufacturing, finance, and many others. And one of the main methods by which machine learning or AI models are being used is in critical decision-making processes. However, despite the high accuracy in many of these different types of AI or ML models, they often operate in what are known as black box conditions. The idea here is that the reasoning behind their predictions is still unclear. And while the high accuracy of these models is still persisting, the lack of clarity behind the reasoning still remains a main challenge, especially when it comes to trust, reliability, and accountability for these types of models. And so the focus of this investigation here today is not only to build and investigate data sets and not only to build and investigate machine learning models, but also to go a step further and explore the idea of explainability as a method to bridge the gap between providing a lot of these types of insights into model behavior and how they operate, really giving developers and stakeholders the ability to validate decisions, ensure that there is compliance with ethical and regulatory standards, and build trust with these different types of AI systems. So when it comes to our approach and methods, the idea here is that explainability can focus on a number of different areas. It could focus on the data that we are using in the sense of what data was used to train that model and how. It could also focus on explainable predictions, looking at the features and weights and how they were used in a given model. But it can also focus on the algorithm. What type of algorithm did we use, the layers, the thresholds, and how that all came together? And so explainability can focus on many different areas. For the purpose of this project, I wanted to not only focus on the data, not only focus on the model, but really take that a step further and investigate the combinations of these as well as how we can explain them in larger systems. And so in this particular project, I selected a number of different data sets, including tabular, text, as well as image, many different models, including discriminative, generative, both open source and closed source, as well as a number of interpretability methods to investigate the different types of combinations here. And the aim was really to highlight the balance, the really important balance between accuracy and interpretability that we can see on the graph on the right-hand side over here, where many highly interpretable models tend to be lower in accuracy, but the higher the accuracy, the less interpretable the model becomes. And so I wanted to choose a really diverse range of data sets, models, and interpretability methods to investigate this phenomena. The first layer of our investigation really focuses on the data. I chose 5 different data sets to investigate within the confines of this project. So starting on the left-hand side, we have the California housing data set. This is specifically aimed towards a regression task. It's tabular data with almost 16,000 observations and 9 different features in total. The second dataset is the Wisconsin breast cancer dataset. This, on the other hand, is a classification task. It's also tabular data, but it has many less observations, but many more features, a little bit different than the California housing dataset we saw a moment ago. The third one is known as the AG News dataset. This is also a classification task. However, this is not tabular data. This is textual data. This is more of a natural language processing approach with almost 127,000 observations. The aim over here is to predict a category for a given piece of text. Next, we have the MNIST dataset. This is a classification task. This is a different type of mode. This is focused on image data with almost 60,000 observations. And the idea here is matching a number to the specific handwritten digit that comes in the form of an image. And then finally, we look at some custom prompting in the form of a large language model. The idea here is also a classification task focused on sentiment. This is textual data with almost 10 different observations, almost 10 to 15 words per observation. And the idea here is to investigate the onset of prompt engineering as it relates to explainability. The next part of our investigation here, the next layer of our investigation, really focuses on the models. For each of the different data sets, we have a model associated with it. Starting on the left-hand side with California housing, we decided to use ridge regression. The idea here is implementing a linear regression model. It implements L2 regularization to reduce overfitting. And the main objective here is to predict the median house price. One item to note is that because of the nature of this model, it does provide feature weights and makes them available to us after the fact for interpretability. Next, with the Wisconsin breast cancer dataset, we implement random forest classification. The idea here is that it is an ensemble-style model. It combines multiple trees for robustness, and the objective is to classify tumors as either malignant or benign. One item to note is because of the nature of this model, we have feature importance metrics made available to us afterwards. Next, for the AG News dataset, we use Distilbert language model. This is a transformer-based model. It is a small to medium language model made available by Hugging Face Framework. And the idea here is classifying news articles. And what it does is it makes a lot of these contextual embeddings available to us afterwards for more interpretability. Next, we have the MNIST datasets, and that is in conjunction with a custom deep learning model. The idea here is that it is a feed-forward neural network. It uses a fully connected layers and ReLU regularization. The idea here is that it classifies handwritten digits, and what it can do is give us pixel-level contributions and make those available after the fact. Finally, we end with some of the custom prompting. The idea here is combining that with GPT-4o large language model, one of the most commonly used language models today. It is a closed source language model in the sense that we do not have the ability to see these features and how it makes these items available from a weights perspective. But it is a multimodal language model, and the idea here is using sentiment analysis for text. And one important item to note is that it does not give us access to weights. We only have access to our input and output of this model. Finally, the next layer of our presentation here today, or our investigation here today, focuses on explainability. We can see that a number of different explainability methods are being implemented with the different datasets and model combinations that we saw earlier. Starting on the left-hand side, we start off with SHAP for regression models. SHAP highlights key features like room count and median income and a number of different others for the California housing datasets, confirming both global trends and feature importance across different types of samples. We can see that it can tell us which contributions were most meaningful and impactful for the decision that it made. Next, we have LIME for classification. LIME offers instance-level insights for the breast cancer classification datasets. It shows which features drove specific malignant versus benign predictions. Finally, we have integrated gradients for complex models. This method visualized pixel contributions in MNIST and token-level attributions in AG News, revealing patterns critical for these types of predictions. What we see next is that when it comes to MNIST, we can see how these pixel-level contributions were impactful towards the model, giving us a sense of how it was able to interpret the different token-level attributions or pixel-level attributions in order to reconstruct these values, specifically the number 7 that you see on the right-hand side. And then finally, when it comes to GPT-4o, our large language model, it's important to note that we do not have access to the internal weights relating to this model. But what we can do is implement token-level importance in the sense that we mask a word multiple times in a sentence, thereby determining how important or impactful a word was to the final model's prediction. When it comes to the results of our experiments that we see here today, we notice that we can think about these from 3 different perspectives. First, when it comes to global and local insights, SHAP and LIME provided some extremely complementary views for tabular datasets, with SHAP focusing on overall trends and LIME offering granular instance-based interpretations. Second, we can think of these from a token and pixel level importance. Integrated gradients highlighted very specific tokens in the AG News datasets, and pixel 11 regions in the MNIST datasets. These were very crucial to model predictions, validating the model's reasoning overall. Finally, we end with sentiment sensitivity. This token level importance quantified how important words in prompts influence GPT-4o's sentiment predictions, and it really showcases explainability even for closed source models when we don't have access to the inner workings of these models. In conclusion, explainability is a necessity. As an AI integrates into many different sensitive domains, explainability becomes or ensures ethical and reliable decision-making processes by shedding light on model reasoning. Many different technique-task pairings that we saw here today, a lot of these different model and datasets require tailored methods. SHAP and LIME for tabular, integrated gradients for unstructured data like text and images. And then finally, one last item that I'd like to end on here is that there's a strong balance between complexity and interpretability. This study emphasized the trade-off between these 2 factors, showing that both simple and complex models both benefit from explainability to varying extents. In conclusion, explainability is a necessity. As an AI integrates into many different sensitive domains, explainability becomes or ensures ethical and reliable decision-making processes by shedding light on model reasoning. Many different technique task pairings that we saw here today, a lot of these different model and data sets require tailored methods. SHAP and LIME for tabular, integrated ingredients for unstructured data like text and images. And then finally, one last item that I'd like to end on here is that there's a strong balance between complexity and interpretability. This study emphasized the trade-off between these two factors, showing that both simple and complex models both benefit from explainability to varying extents. As part of the deliverables relating to this project, I have made the full code base available for this video. You can see everything that went into this project in the code base attached. There's also a detailed report comprising all of the different items relating to my investigations for the data, the models, and the explainability or interpretability assessments, as well as the final summary presentation that you saw in this video. And finally, I will end on a list of references that I used throughout this project and throughout my investigation. So thank you very much for watching. I hope you enjoyed this presentation today.